try this again. I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to give us insight today as we study quotient vector spaces and the first isomorphism theorem, Lord. In your name I pray, Lord Jesus. Amen. All right, so what is a quotient space and what's the first isomorphism theorem? That's what we'd like to talk about today. So to start with, we'll talk about quotient I can't spell. All right, anyway, isomorphism. I need to first define a coset. So here's the definition. If we have V, let V over F be vector space with subspace W, all right, then X plus W is a coset of W, or you might call it a W coset. All right. Now, what do I mean by X plus W? Here, X plus W is just what it sounds like. It's the set X plus little w such that little w is in W, right? So at the start of this section, I define how we can add sets and also how we can scale or multiply sets, I think. I guess I don't have that, but you could do that too. All right. So, okay, so like, for example, we could think about, here's y and x. We're talking about v equals to R2, right? I could think about w equal to the span of, I don't know, like E1 plus E2, right? Also known as 1, 1. I don't know why I wrote it that way. It's more writing. That was kind of dumb, right? So you guys can picture, what does W look like? It's just this, right? That's W. So what's X plus W? If I have X, equals to A comma B, right? Then X plus W in this context is, well, wherever AB is, I don't know. Maybe it's here, right? It's, what is it? It's like, right? Let me just say what it is a parallel line to W. Right? And so if we adjust the value of A and B, right, we're going to get all possible parallel lines, and they'd fill out the plane, right? So we can think of R2 as like the union of all these cosets, right? We could think of R2 as the union of these cosets. All right. Another example you might think about is something like, we could have Rn be the vector space, and A be an m by n matrix, right? Then the null space of A is a subspace of Rn, right? And, I could kind of picture that much like I just pictured the other one, right? Like, this is null A, I'm not very good at drawing I mean, I could attempt the picture in 3 dimensions if you'd like, you know. I'm probably going to regret this. You know, maybe in 3 dimensions, W is a subspace, right? So perhaps it looks like this. So here's my null space. I'm calling that W for the sake of discussion, right? Then if you have another coset, it's going to be like a parallel plane, all right? Here's, you know, A comma B comma C, I guess, plus W in this context. If I'm talking about R3, apparently. Yeah. We'll make it a square matrix just for the sake of things being nice. But we can be a little bit more abstract. I mean, if you like, we could think about, you know, if we're thinking about like AX equals to B, then you know what the general solution looks like. What? Like X is equal to, you know, like the particular solution plus the homogeneous solution, right? Where the homogeneous solution is an element of what? What's the structure of the solution set of m equations and n unknowns? It's the particular solution plus the homogeneous solution. The homogeneous solution is an element of the null space, right? And so, in other words, X is an element of the coset that's formed by the particular solution plus the null space of A. So we could use coset, the idea of a coset, to understand our solution sets from before. Our solution sets form a coset, actually. Right? Now, is the choice of the... sorry, people not here. I meant to move the camera over, my bad. Is there just one particular solution for a non-homogeneous problem? Well, no, right? There are infinitely many different choices for a particular solution, right? So this X here, as we look at this, now I moved the camera. This means X is the representative of X plus W, like manifestly so anyway. So over here, this XP is the representative of this coset. You know, all right, let me move on here. So the fundamental proposition deals with the ambiguity of the representative, all right? And like, this is the deal. This is kind of like the thing that makes this challenging. So given W subspace of V, then X plus W is equal to Y plus W if and only if their difference, the difference of the representatives, is actually an element of W. We can judge equality of cosets by whether or not their difference is in the subspace, which is forming the cosets, right? Think about my example 3. We know that the difference of particular solutions is a homogeneous solution, right? So like, if I had this was equal to xp2, right, plus the null space of A, right? For example, this proposition would say, okay, these are only equal if the difference of x sub p and x sub p2, I don't know, I put the 2 up there, that's weird. X sub p2, the difference of x sub p2 and xp must be in the null space, right? that has to be true. If they're actually particular solutions, that means that a times xp is equal to b, and a times xp2 is equal to b. So of course, when I take their difference and multiply by a, I get b minus b, which is 0, which is to say that they're in the null space, right? So that's how that plays. This idea plays together with this example. Up here, right? If I had another plane, right? If I had another potential, another potential coset up here, that was, say, a bar, b bar, c bar plus w, right? When would it be true that the green coset and the red coset are actually the same one? What you would need, think about it geometrically, is that the difference of a, b, c and a bar, b bar, c bar would have to be what? It would have to be an element of w, right? That would mean that the separation vector between this point and that point, right? This separation vector, yeah? Which I'll call r. It would mean that r lies tangent to w. That would mean that's what it would take for those two parallel planes to actually be the same plane. Is if the difference of the representatives was actually tangent to both of them. I mean, if it was actually in the w space, that would mean that they're actually the same thing. Okay, anyway, we can prove this proposition, so let's do that. So is this an if and only if? Which way do you guys want to start with? Let's start with the forward implication. Suppose that x plus w is equal to y plus w, right? All right, then x plus w is an element of y plus w, right? Not x plus w. See, this is already wrong. I would take tons of points off your test if you did this. Like, I would bleed you dry. You have no chance to survive. That means that x, excuse me, so this means x plus w is a subset of y plus w, right? Then x plus 0 is an element of x plus w, since what? W is a subspace of V, and 0 is an element of W, right? Like, okay, let us set this aside as a lemma that we will use again and again. Lemma, x is an element of x plus W. We just proved that lemma right there. Let's remember this, so I don't have to keep doing that. So what does that give me? So x is an element of x plus w, which, by the way, is a subset of y plus w. What's that mean? Thus, there exists little w naught, let's say, in w, for which what? X is equal to y plus little w naught. That's what it means to be in this set. It means that there's some point in the subspace that when you add that point to y, you get x. But then what does this say? We're almost done, right? Yeah?
X minus y is equal to w naught, so then it's an element of w.
And we're done. Because that's what we're trying to show. We're trying to show the difference of the representatives is in W. And now we accomplished that task. All right? If you're asked to prove something about cosets, you must examine elements. You cannot just hokey pokey add sets. That's assuming the point. We're basically trying to justify our ability to do certain operations on sets, but we have to work through elements before we get to that, all right? So let us continue on here. So next up, the other direction, right? So we go the other way. We assume that x minus y is an element of W. Thus, x minus y is equal to w naught for some W naught in W, right? Thus, x is equal to y plus W naught, which is an element of y plus W. So we know that. Great. Now what are we trying to prove? I mean, that's true, but we're just kind of stick a pin in that. We'll use that in a second. Let's think about what we're trying to prove. We're trying to prove this, right? So what should we do? If we're trying to prove set equality, let's suppose, let's use a different letter altogether. Z is an element of x plus w, right? What's my goal? My goal is to show that z is also an element of y plus w, right? You guys remember this stuff from Math 200, kind of, sort of? This is a little bit different because we got all this vector space structure we're working with now, right? So it's like a little bit more refined. Like the Math 200 discussion is a little bit more kind of like bare bones in some sense. Okay, so that means what?
Z is an element of y plus w naught plus...
Oh, hold on. Come back to that. Thus, there is something in here, right? Like, let's use a different, like W1, right? There's a W1 in W such that what? Z equals to x plus W1, right? Hence, now we'll do what you're, now let's do what you were saying. Z is equal to what? X plus W1, but you said that's equal to what?
y plus w naught plus w1.
Very good. Which is an element of what?
Y plus w.
Y plus W. Why? Since W naught comma W1 in W, a subspace of V, implies that their sum is in W again, right? We have to have the subspace property to make this go, right? If W wasn't a subspace, you wouldn't know that the sum of the W naught and the W1 was again in W. But we do, because W is a subspace, right? And what have we shown? Well, we've shown Z is an element of Y plus W, right? But Z was arbitrary. Consequently, X plus W is a subset of Y plus W. And by symmetry, right? Y plus W is a subset of X plus W. Hence, X plus W is equal to Y plus W. Do you understand the symmetry I'm claiming here? I'm saying there's no difference between X and Y in this statement of the proof. So, oh well. We could make the same argument juxtaposing the roles of X and Y, right? I mean, we'd have to trade W naught for like minus W naught, because, I mean, something like that, I guess. Like, you'd have Y is equal to X minus W naught instead. You'd have to substitute Y for X minus W naught in the corresponding argument. But it's clear we could make the same argument, right? Okay, so corollary to this, essentially, X plus W is equal to W if and only if what? X is an element of what? W, right. See if we can prove that. observe that 0 plus w is equal to 0 plus little w, such that w is in w, right? Which is w. Okay? Like, I mean, that's 0 plus, the coset 0 plus w is w again, right? So if x plus w is equal to w, which is equal to 0 plus w, that's true if and only if what? X minus 0 is an element of w, which is what we're trying to prove. So it's like, that's why I say it's a corollary. It's essentially an immediate consequence of our previous proposition, right? Okay. What is the difference between cosets and subspaces, guys? Is there a difference? Yeah.
Wait, wait. Do cosets have to have 0 in them?
No, they don't. Right.
That's my thing.
I think 0 is in the coset if and only if it is the subspace, right? I mean, that's kind of already, if you put the lemma together with the corollary, I think that gives it to us, right? 0, x is an element of x plus w, so 0 is an element of 0 plus w, which is w, right? So 0 is an element of the subspace, and yeah. So, okay, well anyway. So they're related, but they're not the same, right? I mean, like, the way I think of it is cosets are essentially, unless they're the subspace itself, unless they're the 0 coset, so to speak, they're essentially just parallel translates of the subspace. They're like the same size, so to speak, in some sense. But I can't say they're the, I guess I can't say they're the same dimension in the sense of linear algebra, because if 0 is not in the if 0 is not in the coset, it's not a subspace, right? So we can't talk about, we really shouldn't talk about dimension because it's not a subspace. We've not defined dimension in here for that. In the sense of calculus 3, it has the same dimension, like you could parameterize it, right? There's a parameterization of every coset that matches the sort of parameterization of the subspace, all right? All right, let me go on here. So, proposition. So again, we've got, vector space V over field F with subspace W of V. Then for, let's say, x1, x2, y1, and y2 elements of the vector space, and C in the field. I'm gonna number this. If we have that x1 plus w is equal to x2 plus w, and y1 plus w is equal to y2 plus w, right? Then here's the deal. x1 plus y1 plus w is equal to x2 plus y2 plus w. And cx1 plus w is equal to cx2 plus w. Let me put this into words. I guess this was the 1 and this was the 2. All right, fine. So what I'm getting at here, guys, is suppose we have two different representatives for the same coset, right? See what I'm saying? Here, this means that x1 and x2 represent same coset. They're equal, yeah? Likewise, y1 and y2 represent same coset. So what I'm saying then is if you add the first representatives and get a new coset, it's the same thing as if you added the second representatives to obtain a new coset. And likewise over here, it doesn't matter if I do c times x1 or if I do c times x2, I end up with the same coset. Right? Let's prove it. So the proof looks like this. We have x1 plus w equals to x2 plus w, right? That is true if and only if x2 minus x1 is an element of w, right? But x1 plus y1 plus w is equal to x2 plus y2 plus w if and only if what? Oh, I'm sorry. I'm not finished my thought here, have I? There's more preconditions, isn't there? I've only taken stock of half of what we have. What's the other thing we have? And what else? Y1, this piece here, right? That's true if and only if what? The difference of the y's is in an element of w, right? So we're assuming that the, I don't want to keep saying it. So we're assuming that star and star star are given, right? We're assuming star and star star are true, which means that we have the difference of the x's and the difference of the y's are again in w. But we're trying to show is that this is equal to that, right? But that's true if and only if, by the previous proposition, if the difference of what? y2 plus x2 minus y1 plus, I don't know why I wrote it. What's wrong with me? x2 plus y2 minus, x2 plus y2 minus x1 plus y1, right? Which, by the way, is equal to x2 minus x1 plus y2 minus y1 is an element of w. And likewise, cx1 is plus w is equal to cx2 plus w, right? If and only if what? cx1 minus cx2, which by the way is c times, good grief, I'm trying to do 2 minus 1 here. So 2 minus 1, c times x2 minus x1 is an element of w, right? But to conclude, what do we know? Of course, x2 minus x1, y2, well, okay, so we know that x2 minus x1 and x, grief. But we know that x2 minus x1 and y2 minus y1 are elements of w. consequently, the sum, right, and the scalar multiple are elements of W because W is a subspace of V, right? I don't often aim for a biconditional proof, but this feels like a good place to do one. You know? To not do it, we're going to have to like recreate the magic of the proposition earlier. We're going to have to pick an element on one side, prove it's on the other side, and pick an arbitrary element on the right-hand side, prove it's an element on the left-hand side, prove the double containment. Sometimes I do it that way if I have more time, but I just want to do it this way today. So I hope that's clear. What this means then is the answer, right, that we obtain from like number 1 or number 2 is independent of our choice of representative. See, it doesn't matter which representative I use for this given coset, and which representative, which representative I use for the coset x plus w, right? If I use x1 or if I use x2, if I use y1 or y1, whichever one I use, if I add the first ones, or if I add the second ones, I still end up with the same resulting coset. So we can add cosets by adding representatives is what this means. That brings us, in fact, to the concept of quotient vector space. Yeah. So here we go. Definition. We define V by W to be the quotient space of V by W. In particular, as a point set, V by W is the set of all cosets of W. It's a set of all cosets. Let's write that down. So V by W is the set of x plus W such that x is in V. And for all x plus W, y plus W, and C in the field, define x plus W, parentheses here, plus y plus W, and C times x plus W equal to, we simply add the representatives, x plus y plus W, right? And Cx plus W. Whenever we propose operations for a set as alleged vector addition and scalar multiplication, there's a bunch of things that have to go through for these, right? They have to satisfy the axioms of the vector space. The first of those being that these are in fact these are functions, right? So notice that plus, so defined, right, is a mapping from V by W across V by W to V by W, right? And likewise, this scalar multiplication here is a mapping from the field across the quotient space to the quotient space. And these are single valued. Why? That's what we just proved in the previous proposition. That's what the proposition says. It says that these maps are single valued, right? There's more than this, though. Theorem. V by W is a vector space over the field. In fact, you can check that if we define the addition of cosets and the scalar multiplication of cosets as I just did, that in fact gives us the structure of a vector space. And you can look at the proof of that on page 220 to 221. It's not especially inspiring. It's just kind of a drudgery. But look, there's notation that we should introduce. Notation. Our notation, instead of doing x plus w, all right? Instead of that, we could also do this. Bracket x. So this would be the coset represented by x. And likewise, c, all right, so like in this notation then, c times x, right, is really c times x plus w, right? Which is, of course, by definition, cx plus w, which is cx. So in the bracket notation, scalar multiplication looks like this. You just take the number outside and you bring it inside. But understand that this is a shorthand for working with sets of vectors, right? Es bueno? Yeah, good. Now, how do we, so I hope you'll trust me that V by W is in fact a vector space over F. It's unfortunate I've erased my examples. What do you think the dimension is of V mod? We could call this V mod W if that's okay with you guys. That is what it is. We're essentially squashing W to be 0 of the new space. That's the way this behaves, right? Do you see that? I mean, that's probably the one thing I should have talked about in the proof that I just skipped over. Like, what's the 0? What's 0 in the quotient space? You need 0 plus W plus, x plus W to be equal to x plus W for all x plus W, right? So what does this thing have to be? Well, excuse me, I was saying, what is, Let me hypothetically, oh, good grief, I'm sorry, guys. Words. What I'm trying to say here is that this, which of course is just W, plays role of 0 in V by W. And that's easy enough to verify, right? Try adding that coset to any other coset. What do you get? Get right back where you started again, right? 0 plus x gives you back just x again. Right? Oh, so like the other thing I should say here, my bad. In this notation, x plus y is equal to what? Right? This is what addition looks like in the bracket notation. The bracket notation is so nice because we don't have to keep writing w, 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 right? It's not like a professional wrestling match or something. There's really nothing professional about professional wrestling if you think about it. You know? All right. So what I'm trying to tell you is essentially the W is playing the role of 0 in this new space we're creating. All right? And so one of the things we can prove, proposition, is that if W is a subspace of V, and V is finite dimensional, all right, then the dimension of V by W is actually equal to the dimension of V minus the dimension of W. All right? So how does this work? Like, what's the proof of this proposition? Let's sort through it, yeah? Let's let beta sub W, well, let's say V1 through Vk be basis for W, all right? Extend that. Beta sub W to beta equal to V1, Vk, Vk plus 1, Vn for V, right? We can do that because we're assuming that V is finite dimensional. So we're looking for a basis for the quotient space, right? Let's think about this. How does this work? Let X be an element of the vector space. Then it's equal to the sum, I equals 1 to k, of like x sub I, v sub I, plus the sum, I equals k plus 1 to n of x sub I, v sub I, right? And so as we think about x plus w, right? Let me introduce some notation just for a second here. Let's call this piece x. Let's call it y, and let's call this piece over here z. Y is an element of what? Notice that the V1 through Vk are in W, so Y is by construction an element of W. Which tells me, of course, that X minus Y is an element of, well, anyway, Y is an element of W. One thing at a timer. So if I look at y plus z plus w, I can argue that that's equal to z plus w. Why is that? Well, z minus parentheses y plus z is just what? Minus y, which is, by the way, an element of w, right? Going back to my proposition, those cosets are equal because their difference is an element of the subspace. The larger principle here, guys, is one we'd like to use, which is that we can absorb, see this? Y is essentially something in the subspace, so we can suck that into here. Like the subspace eats its own, right? Do you guys ever see The Never-Ending Story? Never mind. It's like the nothing. It just keeps, anyway. So my point here is simply that x plus w, right, it's actually equal to a sum, I equals to k plus 1 to n of, well, x sub I times, well, parentheses, v sub I plus w. In other words, this is an element of the span of v sub I plus w, where k plus 1 is less than or equal to I is less than or equal to n. So, okay, so apparently gamma equal to v k plus 1 dot 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 vn is a spanning set of for v by w. What do you guys think? Is it a basis? I mean, I sure hope it is, because that's what the proposition needs, right? If that's a basis, how many things are in here? So notice that like the number of things in gamma is n minus k. So we can argue that gamma is linearly independent, thus the dimension of v by w is equal to n minus k, which by the way is the dimension of v minus the dimension of w. Sorry, I shortchanged you guys on the details of that, but you'll forgive me. They're in the notes. Okay? I should have made that a homework problem, like prove the linear independence of the basis there. Notice that this is more than a proof. This gives you a roadmap to find the basis for the quotient space, right? What do? Find a basis for your whole space, right? Such that part of the basis lies in the subspace which you're forming the quotient by. And then you simply take everything else. And the representatives of that, everything else, form the basis for your quotient space. So what's the isomorphism theorem? Let me show it to you. I'll just state it today. We won't prove it today, all right? But the first isomorphism theorem says the following. If you look at, we have to define pi. Pi is a mapping from, goodness gracious, I think it's from v to v by w. And here pi of x is x plus w. This is sometimes called the coset map, I think. Or, man, I forgot to name this stupid thing. My bad. Don't tell Dr. Sprano. I'll lose all respect.
We were doing this today.
Are you doing this today? What? It is the quotient map, in fact. Yes, the quotient map. And this is the quotient map. All right, so let's see here. If I can go from like v over here to w. Oh no. Golly, sorry guys. Let me just stay in my lane. So here's the theorem. If we have t, a mapping from v to u, and w is equal to the kernel of t, and that has quotient map pi, all right, then the mapping t bar, which for us is going to be defined from the quotient space of v by w to u, given implicitly by t bar composed with pi is equal to t, is an injection moreover, V mod the kernel of T is isomorphic to T of V, the range of T. So this is the first isomorphism theorem. Let me show you an example of it. So like a good example. I keep using this example, like most of your tests ends up being this one way or another, right? Symmetric and antisymmetric matrices, right? I'm a creature of limited imagination. I keep using these examples over and over again. So the more you know about them, the easier my test gets, I guess. But so like if I look at what if I look at the map T is a mapping from Rn by n, right, to Rn by n. So I'm going to make my V and my U both equal to the vector space, the n by n matrices, right? And let's say that T of A is equal to A plus A transpose for the sake of discussion. All right? I guess this is example 3. Maybe? 4? Oh, woo! Oh, very good. I feel like I accomplished something today. All right, example 4 then. Then what's the kernel of T here? It's A such that A transpose is minus A, right? The kernel is the antisymmetric matrices because those send this, when you put an antisymmetric matrix into this, you get A minus A, which is 0. So the first isomorphism theorem then says that if you take R n by n and you mod by the kernel of T, it's isomorphic to, what is it? The range of T, right? And what is that? What's the range of T here? It's the symmetric n by n's, right? So it's the symmetric n by n's. And that's what the first isomorphism theorem here, it says that basically Rn by n mod the antisymmetric, I don't have a good notation, antisymmetric n by n is going to give you the symmetric n by n matrices. And notice how that plays well with the theorem we just had. Like the n squared minus the dimension of the antisymmetric gives you the dimension of the symmetric, for example. And you could flip-flop this, right? If you take Rn by n mod the symmetric, you get the antisymmetric if you just change this to a minus. Yep.
Wait, why is the range symmetric?
Oh, because give me your favorite symmetric matrix. How about B? Right? B and the symmetric matrices, right? If I take T of B over 2, I get B over 2 plus B over 2 transpose, also known as B over 2 plus B over 2, also known as B. So it's on 2. That's a symmetric matrix. The output's a symmetric matrix. It's twice the symmetrization of A. The symmetrization of A is just A plus A transpose over 2. But I multiplied it by 2. Anyway, we should prove this theorem next time, but it's incredibly useful for producing interesting new isomorphisms, especially as they relate to quotient spaces. Because oftentimes we can recognize something we like as the kernel of a map that's easy to write down, and then this gives us a fast path to isomorphisms that would otherwise be, troublesome to make explicit. Anyway, I shut up. I'll give you